Welcome back. Today we are going to sort of shift gears a little bit and start taking up a new topic which is related to the part of the course which we have not talked in greater detail, and that is the instability. Now, in order to understand instability, we essentially would need a good concept about the intermolecular forces acting between surfaces and particles. In many of the lectures before, we have talked about the existence of van der Waals forces. We have also talked about the potential curve particularly to explain the approach sequence of an atomic force microscope. But we also understand a little bit about the 1/6 attraction and 1/12 repulsion. We also talked a little bit about the fact that between two fundamental particles the scaling is 1 by r to the power 6, and between two interacting surfaces it is of the order of 1 by r square. So, some of these things we already know, and in the first few lectures we also had touched about a little bit about surface tension and other surface related critical phenomena, some examples of which were we talked about Rayleigh instability in I think the 6th or the 7th class. We talked about the existence of Laplace pressure on the different sides of a non-planar liquid surface, which essentially is a consequence of surface tension. We also defined what is an axisymmetric surface and tried to obtained an expression for Laplace pressure for an axisymmetric surface other than the general expression of Laplace pressure in terms of the two orthogonal radii of curvature R1 and R2. Subsequent discussion sort of we took up more in lines of patterning, and the topics we covered included photolithography, then soft lithography, nano imprint lithography, and then we argued that well, we might be knowing all the techniques to make the structures, but it is centrally important to investigate how good or bad your structures are, because you are talking about sub micron and often in sub 100 nanometer lateral length scales the patterns you are making, and the patterns also are of different variety. They can be topographic patterns, they can be chemical patterns. So, it is important that we learned some method to investigate them, and that is the reason we took up atomic force microscope ahead of instability. But there we had to use some of the concepts of intermolecular interaction, because as you understand the AFM operates based on the basic physics of atomic forces. So, we needed to understand them, but now it is time, before we move on to instability, we understand the precise nature of intermolecular forces. We do some bit of quantitative analysis in terms of these intermolecular interactions, try to quantify them, try to understand what are the intermolecular forces which might be present, and then we would sort of quantify in terms of the fact that we are talking about a polymer. So, some of the most of the polymers are apolar. So, polar components of the polar interactions might not be present. Okay. So, these are some of the things that you can expect us to sort of discuss in the next 2 or 3 lectures. So, intermolecular forces, they are forces that act between neighboring particles molecules, particles which can be, let us say, molecules, atoms or ions. Okay. Now, these forces are of course weaker than the intramolecular forces. Now, what are intramolecular forces? I think you should be able to understand. Before I tell, there is another name which immediately will understand what they are. So, intramolecular forces are forces which that hold atoms together in a molecule, and therefore, now no marks for guessing what it is. So, these covers all chemical bonds. So, first thing needs to understand that intermolecular forces are not bonds, they are not bonds. They are distinct from the intramolecular forces or the chemical bonds, as well as the nuclear forces which sort of holds an atom, that is the interaction forces that goes on between the nuclear particles. Okay. The different type of intermolecular forces, we have already talked about some of them, primarily the van der Waals forces, but we will talk about a little bit detail. So, the other important thing is these intermolecular forces can sort of act between, or I would often be using another word interchangeably, the interaction forces, and at times you will find that this is more of a appropriate word, because of the fact that we write intermolecular forces, but then again we are talking about interaction between molecules, atoms or ions. Okay. So, I would prefer that in many cases that we talk about the so called interaction forces rather than intermolecular forces. And the other important reason why probably interaction forces is a better terminology, that soon we will talk about interaction between surfaces. You may be able to recall already that we talked about, when we talked about the interaction between an AFM tip, when we talked about an AFM, we essentially talked about the interaction between the tip and the sample to be scanned, and therefore, we were not talking about the interaction between two molecules or atoms or ions here, but what we were talking about were the interaction between two surfaces. So, it is important that we understand that though interchangeably we might be using the word intermolecular forces, more appropriate would be to use the word interaction forces. So, all these r to the power 6 scaling and all these things, and we have already talked about one specific form of intermolecular forces, and that is the induced dipole type van der Waals forces, which is often or loosely referred to as the van der Waals forces, but more appropriately they are the London forces or the dispersion forces. Why they are dispersion forces you already understand, because we have argued that they remain dispersed within the entire bulk of the matrix. So, it is all instantaneous, it is temporary dipole type interaction. But let us try to sort of figure out or identify what can be the possible interaction or intermolecular forces, and then based on that try to find out that under what settings all these forces are cooperative, okay, or the operational. You might recall that we have identified that this induced dipole type van der Waals forces is the most generic form, because this acts in all types of molecules irrespective of whether they are polar, non-polar, irrespective of the medium that is surrounding them. But there can be other types of forces which can be operational only in specific types of molecules. For example, we have talked about the AB component of surface tension already in one of our initial lectures, which is the acid base component of surface tension, but then one has to understand that this component is present only if you have a polar liquid. Okay. So, we talked that we also, I think we talked about what is a van der Waals liquid, and we argued that a liquid which does not have any polarity. So, gamma plus, if you may recall, so what we argued was that both the gamma plus and gamma minus, both the components are 0 for this specific liquid, and therefore, what happens is the gamma A B component is 0. So, the surface tension is a pure function of the LW or the van der Waals component of surface tension. So, we will identify these type of systems today. So, the different type of intermolecular or the interaction forces would be are as follows. Firstly, we have the van der Waals forces. Second is the electrostatic forces. Interaction or the polar interaction. And there can be various other forces depending on the nature of the solid surface, nature of the liquid. Nature of the force field, etc. So, these forces can be related to steric forces. Why specifically I point it out? Steric forces, as you can identify from the name, these are due to direct interaction between neighboring molecules, or so sort of, or maybe even the different parts of a molecule, and these are predominant in long chain molecules like polymers. Okay. There can be magnetic forces if depending on the situation, if you have a magnetic field and if you have ferromagnetic material or surface. So, there can be various other types of forces, but for our condition what is most important is to talk about some of the aspects of van der Waals forces, and we will also talk a little bit about the electrostatic and the acid base type of forces. So, amongst the van der Waals forces, there are three categories. I think we have briefly talked about it. So, there can be three categories of van der Waals forces. The first one being the permanent dipole, interaction. The second one is permanent dipole induced dipole interaction. And the third one is, of course, the induced dipole interaction. Okay. You may just want to note down that this permanent dipole induced dipole interaction is often referred to as the Debye forces, and these are referred to as the London forces, named after two scientists. Okay. I guess all of you understand what is dipole. It sort of results due to non-uniform distribution of charges on various atoms in a molecule. It is most pronounced in case of polar molecules, where electron density is shared unequally between atoms. Molecular dipole, this is important to remember, is therefore an electrical dipole with an inherent electric field. The dipole is sort of quantified, as you have probably learnt in your undergrad physics itself, or maybe in 12th standard physics. Dipole is quantified in terms of dipole moment. And in terms of, so we understand that this is, we talk about the permanent dipole, which results due to unequal sharing of electron density across atoms, but in absolutely neutral as well as molecules as well as atoms, due to the localization of the electron cloud around the nucleus at any given instance of time, there is the origin of the so called induced dipole, which induces a mirror charge on the neighboring molecule, and there is this which is the origin of the London forces, which we have already talked about. Okay, so, in permanent dipole, interaction. Of course, let me also just mention one particular thing. The strength of the interaction sort of is highest for a permanent dipole. Permanent dipole interaction is followed by the permanent dipole induced dipole interaction, and is lowest in case of induced dipole interaction. So, these are the strongest ones and these are the weakest ones. Important thing to understand that even the permanent dipole type interaction, the magnitude of the interaction forces – are far lower than any chemical bond. So, bonds are much stronger as compared to intermolecular interactions, and amongst the intermolecular interactions, when we talk about the van der Waals forces, there are three. So, we talk about different type of interaction or intermolecular interaction forces. We talk about the van der Waals forces, and for once we are talking now in a little greater detail. So, amongst so van der Waals forces has three types. It is possible to have three types of forces, or in other words, maybe I will put it slightly better as three different types of interactions are loosely clubbed or generically clubbed as van der Waals forces. They are the permanent dipole type interaction, permanent dipole induced dipole type interaction, and the most generic thing, the induced dipole type interaction. Now, if we look back about our course, you will find that we have mostly talked about the induced dipole type interaction. Okay. So, I will give you a few minutes to think over why in our context this particular force is very important, while I talk a little bit about the permanent dipole type and the permanent dipole induced dipole type interaction. So, this type of interaction is electrostatic interaction between permanent dipoles present in a molecule these forces. So, some molecule, an example can be, let us say, a molecule like HCl. These forces sort of tend to align the molecules in a to increase the attraction. The Debye forces or the permanent dipole forces, if we talk about, these appear from induction or polarization. So, here you have already a permanent positive dipole and a negative dipole present in a molecule. It is not, it is the origin or its existence is due to the unequal charge sharing. So, there is so one part of the molecule sort of is electron rich, which has a negative charge localization. The other part is electron deficient, which has a positive charge localization, and the dipole sort of interacts between these two zones. Okay. So, this is important. So, there is no question of any induction, but the moment you talk about the second and the third type of forces, that is the Debye forces and the London forces, there is the question of induction comes in. So, what is important, that one part of the molecule might be rich due to electron deficiency or electron excess electrons, and that induces a negative a mirror charge on a neighboring zone. Okay. So, these appears from induction or polarization of molecules. So, an example can be, a generic example can be interaction of any inert substance with a polar material. or a liquid. So, let us if we consider one of the classic examples is the interaction of argon with HCl. So, we have already talked that HCl is a polar compound, it has permanent dipole, and so the electrons over here of argon are either attracted by the H plus part or repelled by the Cl minus part of HCl. Okay. So, this type of interaction is possible between any polar and non-polar molecules. Okay. The third type of interaction of course, is the induced dipole interaction, and which we have already talked about. It is most generic form. So, it is due to the charge or electron cloud localization at any given instance of time. So, this induces a sort of results in a localized delta minus charge, which sort of induces a mirror charge on the neighboring molecule, which is delta plus, and as a consequence of that there is a attraction that results instantaneous attraction. But this attraction does not result in any sort of a permanent attraction or bonding, because of the fact that this you have to understand that this charge localization is valid at any given instance of time t equal to t 0, and the next moment and the very next moment at t equal to t 1, the position of the charge localization changes. Okay. So, this is the most generic form of fundamental force, because this now I will come to the word can act between apolar molecules. In the previous two cases, that is the permanent dipole type interaction and the Debye forces or the permanent dipole induced dipole type interaction, we saw that the interaction takes place between at least one of the molecules has to be polar. But here the most important thing is that even in apolar molecules where there is no polarity, where there is no permanent dipole present within the molecular structure, these forces can act. What is important to realize that even if you have polar molecules, these forces are present there as well, but they might not be dominant, as their magnitude is, as we have pointed out, is weaker than any interaction that includes or involves a permanent dipole. Therefore, one thing we have always heard, and so this is probably the time to realize it firmly, that this induced dipole type interaction, or the London forces as they are called, or often they are also called the dispersion forces, they are the most fundamental form of interaction. Okay. The other question I posed to you just a few minutes back is that so far in our discussion we have only concentrated on these dispersion forces, and we did not consider in greater detail the other two types of van der Waals forces. I just told you to think over what is the reason for that. The reason for that is that mostly if you observe carefully, we are talking about polymer thin films, that is the course objective. And polymer molecules, you know, they are organic molecules. So, in most cases, I will not say in all cases, but most cases they do not have any polarity. So, the majority of the cases the interaction between them is apolar in nature, and therefore, the van der Waals forces dominate to a large extent. There can be certain other examples. I think it is an appropriate time to highlight few of them. You can have a situation where there are permanent dipole centers within a molecule, but there is no effective permanent dipole of the molecule, and this happens in some symmetric molecules like carbon tetrachloride or type of a thing. So, where because of the presence of chlorine minus ion, there is all the bonds are sort of there is a localization of the electron towards the chlorine end of the molecules. But what is important is that since this molecule has a tetragonal symmetric structure, the polarization sort of cancels out within the molecule itself, and the effectively there is no net dipole present in this type of a molecule. The other important thing what you may think a little bit, and another term that what you have heard from your school days is hydrogen bonding. Not that hydrogen bonds are going to be that greatly important for polymers, but there are several questions which you might have already encountered, or several phenomena which are attributed to hydrogen bonding. One of them is the boiling point of water is pretty high at 100 degree centigrade. The other thing is that water has the highest density at 4 degree centigrade, and issues like that, and in most cases you know that they are attributed to the existence of hydrogen bond. So, question to ask is hydrogen bond a chemical bond, or is hydrogen bond, so you also know that bare hydrogen atom or ion cannot exist in water. So, it is always in the form of an hydroxonium ion H3O plus. The question to ask is hydrogen bond a chemical bond, or it is a permanent dipole type of an interaction. And the answer is, so let us try to find out what is hydrogen bond. It is an attractive force between a lone pair of an electronegative atom and a hydrogen atom which is bonded either to nitrogen, any chemistry book will give you this definition, oxygen or fluorine. In often an hydrogen bond is described as a strong electrostatic dipole-dipole interaction. However, it also has certain features of a covalent bond. As it is directional, stronger than and is stronger than van der Waals interaction. Interactions and produces interatomic distances shorter than van der Waals radii and also involves limited number of interaction partners. Which is sort of which is similar to some sort of valency. Okay. Therefore, you may, without going into any greater detail, may realize that hydrogen bond is somewhere in between a permanent dipole type van der Waals force and an polar chemical bond. So, this is just for your information come learning, I would say, because hydrogen bonds are also very important in many settings, but what we need to understand that they strictly they do not fall into the category of van der Waals forces. Okay. So, to a large extent, since we will be dealing with polymers, we will be focusing on the induced dipole type van der Waals forces, but it is important to note that the attractive interaction. So, the other thing to understand is all the three types of interactions, at least at the molecular level, they are attractive in nature. Between surfaces, we will show that there can be situations, of course, in air or vacuum, even between two surfaces the van der Waals interaction is always attractive, but in presence of a third medium, primarily a liquid medium, we will show that a pure van der Waals interaction between two surfaces. So, two surfaces in a third liquid, each one is completely apolar. So, the entire component of surface energy is van der Waals. So, the liquid is van der Waals liquid, the surfaces are apolar, but you still can have a situation where you can have an effective repulsion which originates from van der Waals forces. But what is important to understand that at the molecular level as well as the interaction between two surfaces in air or vacuum, van der Waals interaction is always attractive. Okay. So, the other important thing to understand that at the molecular level, between molecules, the scaling is 1 by r to the power 6. Okay. And for all the three types of forces, there can be some numerical prefactor which sort of governs the relative strength of the three types of forces. So, the scaling is the relation between the separation distance remains as 1 by r to the power 6, but depending on the precise nature, you can have different settings or you can have different numerical prefactors which takes care of the strength of each of these forces. Okay. So, with this much amount of understanding, so let us do a quick recap. The other important thing is that these electrostatic forces, for example, before I move on, I must have a quick mention about it. So, these electrostatic forces the second type of forces that we talked. These electrostatic forces are operative when at least one of the surfaces carry charge. It will, in that case, it will induce a mirror charge or opposite charge on the other surface. Because of the presence of free mobile ions in a liquid medium. I would probably remove the word induce. It will sort of in that case it will accumulate mirror charge, I would say, in a liquid medium. So, these what it is, I am just coming to it with an example. So, these mobile charges screen the surface charge by accumulating near the surface with opposite charge having these forces are often referred to as the double layer forces. So, what happens is, let us say you have a surface which is in contact with a liquid medium which has free ions. So, both positive and negative ions are there. Let us say the surface is sort of positively charged. So, what happens is, so these ions are sort of so first important thing is there is a liquid medium. So, these free these ions are free to move, and therefore, as a consequence that the ions are free to move or free to sort of orient or position themselves. So, what happens is the surface has positive charge. So, what will happen, this negatively charged ions will sort of migrate close to the surface and they will form a layer close to the surface. So, if you now see the individual word, it sort of makes sense. So, at least one of the surface carries a charge. So, here is a solid surface which carries a charge, and that will accumulate or attract the mirror charges, that is the negative charges. A layer of ions will form along the in close proximity with the surface which has the opposite charges on the other surface because of the presence. So, what is the source of this negatively charged ions? The source of the negatively charged ions is that there are free or mobile ions available in a liquid medium. So, these mobile charges, once they accumulate, they sort of screen the surface charge by accumulating near the surface. So, what does screening in this context mean? It means that now to the liquid, the surface does not appear to be positively charged, but it appears as if effectively the surface has a negative charge. So, what this layer of accumulated ion has done, it has sort of screened the actual surface charge. And what will further happen now, there will be a localized accumulation now of the positively charged ions close to this. Okay. So, and then eventually at the bulk there will be a condition charge neutrality. So, this whole structure close to the surface of the charged surface is known as or referred to as the electric double layer. There are certain critical concepts associated to an electric double layer. I think towards the later end of the course we will talk about zeta potential, Stern layer, and all these concepts. Most likely towards the end of the course we will discuss. Even otherwise, you are welcome. Now that you understand the basic structure of an electric double layer, you are encouraged to have a look at some of these things in the internet or any standard textbook. So, these type of forces also play a very important role. So, let us say you have a layer of a surface which is coated with sodium chloride, let us say it is a salt coated surface which is in contact with water. So, sodium ions are ions are dissolving. So, it has an effective polarity, or any surface, forget about this particular example. So, any surface which has a polarity will and is in contact with a polar liquid or which has ions. So, let us say that a dilute solution of salt is in contact with a polar surface. So, you have a surface, just withdraw that example. So, you have a polar surface which is in contact with a dilute solution of, let us say, salt. Therefore, you have these ions which are freely moving in the liquid medium. So, what is going to happen? Ideally, in this liquid medium, this concentration of the ions is uniformly distributed, and that okay. But see, close to the polar surface, what is going to happen is depending on the nature of the surface charge, either the, so if it is a positively charged surface, the chloride ions will accumulate close to the surface. If it is a negatively charged surface, the sodium ions will accumulate towards the surface. So, this is and it results to the formation of an electric double layer. So, this results in some sort of an additional surface potential which is quantified in terms of the zeta potential, which can be physically measured in experiments using an instrument called zeta meter. So, this gives you an idea about the strength of the electric double layer forces. But then coming back to our system, which is the polymers. So, now even if you have a scenario that you have a polymer thin film, over which let us say a salt solution is flowing. Since the polymer surface does not have any polarity, so there will be no electric double layer formation, and because of the fact that there is no driving force for either of the ions, either positively charged or negatively charged, to sort of migrate, preferentially migrate towards the surface. Therefore, we understand that electrostatic forces can be very, very important in many settings, but for a polymer thin film, particularly what we are talking about, polymer thin film in air, or because most of the patternings we have done, we have talked about essentially a layer of polymer thin film, and then we have patterned it with a stamp, master, or whatever. These forces are rather insignificant. Therefore, we need to focus most on the van der Waals forces or the London forces, or the dispersion forces, because in polymer they are charge neutral, there is no permanent dipole, but these forces, interaction forces, are always going to be present there. Of course, the additional thing that one should not neglect, and we have talked about it a little bit in terms when we were discussing about nano imprint lithography. If you remember, we talked about the velocity profile and the stress accumulation in nano imprint lithography. So, these are all attributed to the longer chain molecules, which are the polymer molecules are long chain molecules, even the linear chain molecules are long chain. Of course, there can be additional complexities arising because of the fact, because of cross linking. We have talked a great deal about Silgard 184 or elastomers, which are cross linkable. So, there are additional interactions that originate. So, now once a matrix is cross linked, so it's now physically interconnected, the molecules are physically interconnected, and depending on the rheology of the system or the viscoelasticity, this cross-link matrix can be flexible, can be rigid. So, you can have room temperature elasticity and all these effects. But the next thing that we are going to talk about is the spontaneous instability in a liquid or a viscoelastic polymer thin film. The most important thing that is going to sort of come up, or the most important interaction force that is going to come up, is the van der Waals forces or the dispersion forces. So, therefore, we will be focusing in our subsequent class on this specific aspect, that is the induced dipole type interaction. So, this is how we plan to sort of bridge the story. So, we first talk about or identify about the nature of induced, or the nature of London forces between two atoms, which we know is 1 by r to the power 6, the attractive part, and also there is a repulsive part, which is 1 by r to the power 12. Then, so this is the first thing which we already understand. Then the next thing that we take up in the next lecture itself is the nature of interaction between two surfaces. Subsequently, once we understand the nature of interaction between two surfaces, so first we talk about the interaction of two blocks, let us say, of 1 and 2. So, let us say these are two molecules of 1 and 2, then we talk about the interaction between two blocks of 1 and 2, and then eventually we will talk about this type of interaction. So, we have a film of material 1, which can be a self-standing film. So, here also we have two surfaces, the two film air interfaces, what is the nature of interaction between them, or a more generic case, we have already talked about a spin coated or a dip coated thin film. So, you have a film of liquid layer 1 which is coated on a substrate. Okay. So, how the interaction between this and this interface governs the evolution dynamics or the stability of a system. These are some of the things which we are going to look up in the subsequent couple of lectures, and the standing basis point or the fundamental concept which is based on the induced dipole interaction between molecules. Thank you.